We have arrived at the quantum realm, the bedrock of modern physics, and perhaps our greatest chance of unraveling the enigmas of time itself. In this realm, particles can exist in two locations at once, defy expectations, and communicate instantaneously across great distances. Unlike the vastness of spaceships and theoretical wormholes, the scale of the universe is much smaller. The rules we've always taken for granted might be incomplete, as these apparently impossible ideas push the boundaries of what we understand about time. For example, have you heard of quantum entanglement, where two particles remain connected no matter how far apart they are? Or retrocausality, where future events could influence the past? Time isn't just a scientific concept, though. Time is something we encounter constantly, isn't it? Is there a way to control its speed, alter its direction, or even turn it backwards? The quantum realm opens our eyes to fascinating but terrifying possibilities, such as altering the very nature of time and discovering parallel universes. If you're up for an exciting adventure, I'll be your guide as we unravel the mysteries of quantum mechanics and how they're influencing our. Welcome to this captivating exploration of quantum physics and time travel. Time seems like a simple concept in our daily lives. An alarm clock wakes us up, the minutes pass, and hours turn into days. It's a smooth progression that helps us organize our lives in a linear and predictable fashion. However, time is more than just this steady march. It's an element of the universe that, when viewed through the prism of quantum mechanics, time challenges our intuitive understanding and questions our very conception of what it is. What if, instead, time is not precisely what we think it is? To delve into this question, it is necessary to first grasp the conventional definition of time from a physics standpoint. According to this view, time is interwoven with the fabric of spacetime, which serves as the stage upon which the universe performs its play. This classical view of time emerged in the works of Isaac Newton. Newtonian physics posited that time is absolute, unchanging, and universal. However, with the development of Einstein's theory of relativity, this view of time underwent a dramatic change. According to Einstein, time is relative, and it does not flow uniformly as Newton had believed. Rather, it stretches and compresses depending on variables such as gravity and velocity. This groundbreaking perspective on time is, however, being questioned by the peculiar and frequently perplexing realm of quantum mechanics. For example, as one approaches a massive object, such as a black hole, the passage of time slows down owing to the enormous gravitational pull. Similarly, when one travels at speeds close to the speed of light, time dilates and ticks more slowly relative to someone standing still. The core of quantum mechanics is dealing with probabilities and possibilities rather than certainties. Events in the quantum realm are not deterministic like in classical physics, but are governed by a fuzzy world of likelihoods. This ambiguity complicates our traditional understanding of time. One element of quantum mechanics is the uncertainty principle, which is often cited in relation to position and momentum. But there is another intriguing concept at the quantum level is superposition. A quantum particle can exist in multiple states simultaneously until it is observed or measured. This phenomenon raises fascinating questions and is explained by the time-energy uncertainty principle, which states that the more precisely you measure one variable, like energy, the less precisely you can know the other. In this case, time is not as solid as it seemed. It is blurry and uncertain. The existence of multiple timelines or moments at once raises intriguing theoretical questions regarding the nature of time and whether we perceive it in its entirety or in slices. Concepts based on quantum peculiarities seek to further dissect and reconstruct our comprehension of time. One such revolutionary idea is the block universe theory, which holds that time is not a flowing river, but This framework allows you to see time not as something that passes, but as something that is fixed, like your birth right now, and events in the far future are all a part of this frozen tapestry of space-time. On the other hand, some physicists have proposed the idea that time itself does not exist fundamentally, but rather as an emergent property a result of profound underlying processes that we do not completely comprehend just yet. Entangled particles stay connected regardless of how far apart they are. A change in the state of one instantly affects the other no matter the distance. This phenomenon raises an intriguing thought about whether entanglement can connect particles across vast stretches of space. It is not fundamental to the fabric of the universe, but it is an emergent phenomenon that arises from the interactions of particles in our universe. While this theory is still in its early stages, it highlights the possibility that quantum mechanics could reshape our understanding of time through experiments, theory, and intriguing conjecture. Whether it's the block universe, the uncertainty of quantum measurements, or the strange connectivity of entanglement, one thing is certain: time is complex. May not be as simple as a simple clock ticks away. Rather, it appears to be an intricate and ever-changing part of our universe that contains mysteries that we are only just starting to discover. Picture this. What if a particle could squeeze through a solid without collapsing? This isn't science fiction. It's the concept of quantum tunneling, and it's making us rethink our entire understanding of the cosmos. Particles in the quantum realm don't follow the same rules as those in classical physics. So instead of sliding back down a hill if they don't have enough energy to climb it, they can borrow energy, pass through the barrier as if it weren't there, and then return it. This phenomenon is almost like quantum levitation, except that particles don't have mass. The intriguing and perplexing aspect of quantum tunneling is that particles can traverse obstacles that they appear to lack the energy to overcome. This behavior is made possible by the probabilistic nature of quantum mechanics, which states that particles do not have fixed positions or paths, but rather exist as waves of probabilities. In other words, at the quantum level, particles aren't static. They exist in a fuzzy state where they're. Since precise location and energy cannot be determined with 100% certainty, according to Heisenberg's uncertainty principle, there's a non-zero chance that the wave function of a particular particle, which indicates its potential location, goes beyond the physical barrier. This probability enables the particle to tunnel through the barrier in a manner that defies all conventional rules while still obeying the laws of quantum physics. You may be asking how this works. There is a stark contrast in the behavior of the macro and quantum worlds due to the scale-dependent nature of quantum effects. Large objects, such as a basketball or a car, have an incredibly low probability of tunneling, making it practically impossible for them to do so within the observable lifetime of the universe. As for why we don't see objects around us tunneling through walls, that's a great question. To understand quantum tunneling, it's helpful to think about electrons as tiny particles that exist inside of atoms and are limited to specific energy levels or orbits. In order for an electron to leave its atom, it usually needs to gain enough energy, like heat or light, to overcome its binding force. However, there are situations in which electrons can tunnel through this energy barrier instead of acquiring the required energy, and they can suddenly appear on the other side. Quantum tunneling allows electrons to jump across thin barriers between semiconductor materials, which is essential to the functioning of transistors, the building blocks of practically every computer, smartphone, and electronic device you use today. So why does this matter? The answer is that quantum tunneling has innumerable applications in modern science and technology. One prime example is semiconductors. Another incredible use of quantum tunneling is in the sun's inner workings, where extremely high temperatures and pressures cause hydrogen nuclei to fuse into helium. This process is called nuclear fusion. In a classical model, the energy needed to overcome the repulsive forces between the particles would be far higher than what the sun's core could provide. However, with the help of quantum tunneling, this is no longer the case. The ability of nuclei to essentially bypass these barriers enables nuclear fusion, which in turn powers the sun's ability to shine. Now, let's take this concept to the next level. Could quantum tunneling have implications for time itself? This is an exciting question that has scientists and science fiction enthusiasts buzzing. Concepts like quantum entanglement and tunneling have. Theoretical models propose intriguing possibilities, but there is currently no experimental evidence that would allow us to use tunneling for time manipulation. Despite numerous particle-level observations of quantum tunneling, the connection to time travel remains purely hypothetical. This has sparked speculation about faster-than-light travel and the possibility of manipulating the past or future. It's obvious, but groundbreaking research keeps pushing the boundaries of what we can imagine and understand. Quantum tunneling, for example, has become an indispensable tool for exploring the universe. It challenges our classical worldview and gives birth to innovations that transform our lives, from advancing basic physics research to creating advanced quantum technologies. One question that feels lifted is whether decisions made today can influence the past. Delayed choice experiments are a prime example of how quantum mechanics challenges our perception of reality. At its core, they ask a simple yet baffling question: do delayed outcomes occur in real-life situations, or is this just a fiction? In order to better understand this, let's recall the famous double-slit experiment. If you're familiar with quantum mechanics, this experiment may sound familiar. To refresh your memory, it involved firing tiny particles like photons at a barrier with two slits. Placing a screen behind the barrier allowed the particles to pass through. The choices we make now determine how things behaved in the past. Photograph the spot where the particles touch down. You'll observe an unusual phenomenon. Instead of acting like individual particles, they form an interference pattern resembling overlapping waves in a pond. However, when detectors are placed at the slits to determine which slit a particle goes through, the pattern vanishes and the particles behave, well, like particles. This experiment was already bizarre enough, but physicist John Archie Wheeler proposed an even more bizarre delayed choice experiment in the. When physicists performed variations of the experiment in the 1970s, Wheeler came up with a daring and brilliant idea. What if we wait to see the particle until it's passed through the slits? Logic would dictate that the photon's behavior should already be decided by the time it reaches the slits, but in quantum mechanics, logic doesn't always work as we expect it to. Applying Wheeler's thought experiment to real-life scenarios yielded astonishing results. Adding detectors made the photon behave like a particle, while not doing so caused it to behave like a wave. It's as if the photon anticipated what was coming and adapted its actions accordingly. Now, before we delve too deeply into the implications of this, it's important to understand what it does and does not mean. The results of delayed choice experiments do not indicate time travel or the ability to physically alter the past. Rather, they show how strange quantum mechanics is. The results contradict our classical view of cause and effect, implying that events may not follow the linear flow of time at the quantum level. Physicists do not see these results as proof of particles traveling back in time, but rather as proof of the fundamental weirdness of quantum. Delayed choice experiments are intriguing because they relate to larger questions about the nature of time. In classical thinking, we perceive time as a simple succession of past events. In quantum mechanics, however, this view is challenged by the fact that a particle's behavior, whether it behaves like a wave or a particle, depends on how we decide to measure it. The past and the future seem to be moving in a straight line, but delayed choice experiments suggest that this might not be the case on a quantum scale. Time and space could be more interconnected than we think, though not in ways that violate causality. For example, these results make us question the traditional order of cause and effect. For example, we know that touching a hot stove causes a burn, not the other way around. The behavior of a quantum particle is affected by the actions of the observer, even if those actions happen after the particle has already made its initial state. This phenomenon still perplexes scientists and shows that the universe works in ways we are just starting to comprehend. But what good is all this for? Well, delayed choice experiments help us understand the basis of quantum mechanics, which is practical applications. Potential technological ramifications, such as the fact that our understanding of quantum measurement has been enhanced thanks to this study. Quantum computers, for example, are based on the idea of quantum bits, also known as qubits, which can exist in two states at once, 0 and 1. This idea stems from the same principles of uncertainty and observation that guided the choice experiment. And who knows, maybe one day the principles revealed by these experiments will inform technologies that we can't even begin to fathom. Today, in the same way that classical physics gave birth to steam engines and electricity, quantum physics is preparing the way for the next revolution in computing, communication, and beyond. You might be feeling a little confused about how the universe works, but that's okay. That's precisely what makes quantum mechanics so intriguing. Delayed choice experiments show us that science isn't only about finding answers, but also about asking better questions. For example, what does it mean for particles to lack defined behavior until? Every now and then, phenomena like the delayed choice experiment provide a glimpse into a universe far stranger and more complex than what our senses might suggest. It's a humbling thought to consider how these findings relate to our everyday experiences, which are based on classical physics. Furthermore, how does this relate to the nature of reality itself? It's a thought-provoking concept that could inspire a new way of looking at the universe. One of the most perplexing ideas in quantum mechanics is the quantum eraser, which sounds like something out of science fiction. The idea is that actively erasing information could impact an event that has already occurred. This phenomenon challenges our very understanding of the universe. The quantum eraser is an experiment that, to the uninitiated, appears to be a magical rewriting of reality through the act of forgetting. However, like all things scientific, there is a deeper logical explanation lurking in the chaos. To understand this phenomenon, one must first understand the concept of information, which is central to quantum mechanics. Consider the famous double-slit experiment, in which a single particle, like when a photon or electron is shot toward the barrier with two narrow slits, it acts like a wave passing through both slits and creating an interference pattern on screen. However, as soon as we figure out which slit the particle goes through, its wave-like behavior collapses into a particle and the interference pattern vanishes. Knowing the which path completely alters the experiment's outcome. The possibilities are reduced to a single clear event when a detector is placed by the slits. Now, what happens if we erase the information about the particle's path? When the information about the particle's path is sealed or destroyed after it travels, but before its final result is observed, wave-like behavior and interference patterns can return, as if the particle forgot which path it took. This is where the quantum eraser comes into play. In this particular experiment, particles are released and pass through a double-slit barrier, but this time the experimental setup incorporates paired photons. One photon, known as the signal photon, travels to a detector. Meanwhile, the paired photon, called the idler photon, takes a different path to a secondary detector. Here's the kicker: the information about which slit the signal photon traveled through can be inferred based on the idler photon's path in some branches of this setup. However, if this WIT path information is erased, say, by routing the idler photons in such a way that this information becomes unknowable, the interference pattern can reappear in the signal. It's worth noting that the decision to erase the information can be made after the signal photons have already reached the detector. In this way, it's as if the future influences the behavior of the particles during their earlier flight. While this may sound like time travel, it's actually just a quirk of quantum mechanics. The real trick is the intricate relationship between entangled quantum particles and the shared wave function reveals that quantum eraser does not rewrite history, but rather tells a consistent story across space and time, with results that match up with present observations, giving the impression of retroactivity. This theory also offers a unique perspective on entanglement, one of the most elusive principles in quantum mechanics. When particles are entangled, their properties are so closely linked that the measurement of one instantaneously determines the properties of the other, regardless of their distance in space. To demonstrate how entanglement and the collapse of probabilities into fixed outcomes behave, the delayed choice quantum eraser takes advantage of this connection. It's like a cosmic magician showing us one thing while hiding the mechanisms behind the curtain. The potential applications of this principle, although theoretical at this stage, spark imagination. Quantum eraser could allow breakthroughs in our understanding of quantum information manipulation. It might prove relevant to quantum memory mechanisms where erasing and rewriting entangled states play critical roles. Quantum computers, which rely heavily on controlling particle states and information, could also tap into principles adjacent to eraser setups, and in quantum communication eraser schemes might help refine how quantum information encoded in particles is managed and transmitted securely. However, while quantum mechanics is a fascinating subject, reality often limits our loftier ambitions. Despite its complexity, quantum mechanics has a captivating allure. It shows us that our classical worldview has flaws and that the rules governing the universe are far more subtle, strange, and interconnected than we had imagined. For every answer it seems to offer, it leaves us with more questions. The tension between uncertainty and clarity is palpable. The known and the unknown is what makes quantum physics and concepts like quantum eraser so irresistibly music. Fascinating. What if the choices you make tomorrow could ripple backward and alter the outcomes of yesterday? What if the decisions yet to be made already hold sway over the events you thought were set in stone? These aren't abstract musings from the realm of science fiction, but rather fascinating questions born from the intricate study of quantum physics. This is retrocausality, a mind-bending concept. Retrocausality is a concept that shakes up our fundamental understanding of cause and effect. It suggests something both unsettling and exciting. That time, which we often picture as an unyielding arrow, might actually be more like a flowing river, capable of bending, doubling back, or even blurring its boundaries completely. This idea that causation isn't necessarily one way is introduced by retrocausality. This concept may sound like philosophical speculation, but it is actually based on cutting-edge quantum mechanics. In this field, the concept of time becomes very fluid and nebulous, and using quantum mechanics as a backdrop, retrocausality asks a question that may seem ridiculous in our everyday lives. Could the act of observing or measuring something in? At first glance, it seems like the future can't impact its past. After all, when you drop a coffee cup, it shatters on the floor. It's not like you can magically reshape the shards into a perfect cup by pretending the fall never happened. Our world views time as linear, with causes leading to effects in a predictable march. However, when you delve into quantum mechanics, the rules governing cause and effect seem less immutable. Retrocausality finds its most interesting playground in light's tiniest particles, photons. Imagine a particle of light behaving differently depending on something that happens to it after it's already been emitted. If you think that sounds outrageous, you're not alone. It's the kind of discovery that makes researchers scratch their heads and physicists rethink centuries-old assumptions about the mechanics of the universe. Take, for instance, the experiments surrounding quantum entanglement. Picture a pair of entangled photons are entangled particles that are affected by each other's states regardless of their distance from each other. What makes this phenomenon even more bizarre is that when we measure the polarity of one entangled photon in the present, it appears to determine the state of its partner photon in the past, even though that partner photon has already existed. It's as if information about future measurements travels backward through time to clarify the pair's behavior. What's even more bizarre is the delayed choice effect. In the quantum eraser experiment, researchers split and recombine photon beams to see how their behavior changes depending on whether scientists decide to observe them. Here's the catch. A decision made in the future about whether to observe the photons seems to retroactively dictate whether they travel as particles or interfere as waves in the past. This makes the past, which many of us imagine as a fixed and unchangeable record, appear strangely malleable in these experiments. But wait, before we get ahead of ourselves and imagine a reality where revisiting past mistakes becomes as easy as editing a Word document, retrocausality has its limits, its applications and implications so far remain firmly rooted within the quantum world. This isn't about rewriting personal history or time traveling to correct glob injustices. There are no futuristic scenes of scientists zipping through wormholes to meddle with historical events. instead retrocausality touches on. Subtle behaviors of particles at minuscule scales nudging us closer to unraveling the mysteries of time. And what does this mean for our current understanding of causality and retrocausality? This is a controversial and delicate concept that physicists are still trying to figure out. For the time being, its potential practical applications are just rumblings in the wind. The role of retrocausality in the classical systems that govern our macroscopic reality is still up for debate, but its broader implications for quantum mechanics and our understanding of time are undeniable. In the end, how will causality change the way we construct theories of the cosmos? How will it change the frameworks through which we perceive reality, causality, and existence? Seeking these answers is more than just a mental exercise. It's a demonstration of our ability to challenge the formerly accepted status quo. The question that has baffled physicists and philosophers for decades is what happens when we measure something at the quantum level, the smallest scale possible. It's like flipping a coin. It's either heads or tails, no middle ground. In the quantum world, particles exist in multiple states at once, only choosing one when observed. How does this strange phenomenon fit into our understanding of the universe? Here, a bold idea comes into play, one that could completely transform our perception of reality. In the 1950s, when quantum mechanics had just begun to transform our understanding of the microscopic cosmos, even its most brilliant pioneers were at a loss to explain some phenomena. Enter Hugh Everett, a young Princeton doctoral student who made the bold proposal that every quantum event could create a new universe. To illustrate his point, consider the following scenario. Instead of just getting heads or tails, the act of flipping the coin could split reality in two, creating a new universe. Exists where it lands heads, and another where it lands tails. Each represents a different outcome, neither one more real than the other. Everett's idea, later coined the many worlds interpretation, defied the conventional thinking of his time. Instead of collapsing into a single outcome, like a wave crashing against the shore, the quantum wave function never collapses. Instead, it branches endlessly, creating parallel universes for every possibility. The implications of this theory are mind-blowing. Think about your everyday and the innumerable choices you face. Should I take the long way around or go straight? Should I take that new job offer or remain where I am? Everett claims that with every decision you make, a parallel universe is born, where you live a completely different life. In one universe, you could be a CEO in Tokyo, in another a Parisian artist. It's a fascinating and disorienting thought that challenges our fundamental assumptions. Think about it. Instead of messing with your own timeline and risking paradoxes like the infamous grandfather paradox, where your interference could prevent your own birth, you could just jump to a universe where events unfold naturally based on your past visits. That's how the many worlds interpretation of time travel changes our understanding of something even wilder than wilder time travel. Your actions picture it this way: you miss an important deadline at work and wish you could reverse time to meet it rather than rewinding the clock on your original timeline. The many worlds and interpretation suggests you could move to a universe where you did meet the deadline. Your original timeline remains untouched, while you begin anew in an alternate reality. This reshapes the age-old concept of paradoxes in the grandfather paradox. If you traveled to the past and prevented your grandfather from meeting your grandmother, how could you exist to make the trip to begin with? The many worlds interpretation resolves this conundrum. By preventing the meeting, you create a new universe where you were never born, but your original universe and your existence within it remains intact. It's not so much changing the past as it is choosing a different thread in the infinite fabric of existence. This makes time travel less of a disruption and more of a detour, seamlessly sidestepping the philosophical headaches that have plagued the idea for centuries. Still, there are a lot of problems with the theory. For example, if you can't go back to your original timeline, is it still time travel? Another issue is how to choose which universe to jump to. The possibilities are endless, but so is the difficulty of finding a specific grain of sand on an endless beach. and scientists still haven't figured out whether these parallel universes are anything more than just math. Ideas like time travel, alternate realities, and quantum pathways spark our imaginations like few others, but they also challenge our grasp of the universe and make us reevaluate our beliefs about the nature of reality, free will, and the nature of reality itself. Without tangible proof or a means to communicate with these other realms, these theories could remain purely theoretical. It's more than just a scientific theory. It's a way of looking at the universe that opens our minds to new possibilities. Perhaps this is the closest thing we've found to seeing through the illusion of reality. Music. Picture a world where the past and future don't always coincide, and where the lines between what's real and what's not blur into a bizarre dance of possibilities. This isn't the trailer for some science fiction blockbuster. It's the basis of a mind-bending concept in physics known as closed timelike curves. Here we will shed light on this intriguing intersection between the mysterious principles of quantum mechanics and the equations of general relativity, with a focus on scientifically grounded theories that avoid speculative fiction. These theoretical pathways suggest that spacetime can fold and bend upon itself, allowing for loops in time. Their roots are in Einstein's groundbreaking work, but the implications of closed timelike curves go well beyond the domain of classical physics. On a journey through a universe stranger and more captivating than any screenplay, Einstein's general theory of relativity is the starting point for closed timelike curves. This groundbreaking framework explains how massive objects impact spacetime, distorting it like a bowling ball on a rubber sheet. Theoretically, under certain mathematical conditions, this distortion of spacetime could theoretically permit loops, where the timeline bends and reconnects to itself. Picture this. You're tracing a path through spacetime that leads you. Returning to your starting point, not in space but in time itself, such pathways suggest the possibility of existing alongside previous selves or even traveling back in time. One prominent early proponent, Kurt Gödel, put forth a spinning universe solution where such loops could emerge naturally. Frank Tipler also investigated the theoretical construct of Tipler cylinders, which are infinitely long rotating objects that are said to produce such loops. While these models are exciting for the imagination, they raise serious questions about. In light of nature's apparent openness to time loops beyond the theoretical boundaries of closed timelike curves, we can't help but wonder, is it possible for an object or a person to travel back in time? If so, how? This intriguing prospect opens up a world of paradoxes that test our intuition. For instance, consider the grandfather paradox. If a time traveler intervenes to stop their grandparents from meeting, for example, they run the risk of erasing their own existence. There is no clear rule in general relativity that forbids such loops, so physicists are left to wonder if they are just a logical anomaly, or if there is some hidden truth about the universe. Nevertheless, in order to create the physical conditions for closed timelike curves, theoretical models propose the existence of exotic matter with a negative energy density, which goes against the grain of conventional physics. Some parts of negative energy have already been tentatively explored in quantum mechanics. Its existence remains speculative at best. The energy requirements for bending spacetime into a loop are astronomically high, far beyond anything our current technology could achieve. This is where the principles of quantum mechanics provide an intriguing avenue of exploration. Unlike the deterministic framework of classical physics, quantum mechanics introduces probabilities and uncertainties, offering a drastically different canvas for studying systems with closed timelike curves. It's here. Closed timelike curves, according to the Deutsch model, named after physicist David Deutsch, could avoid paradoxes by following probabilistic rules instead of deterministic ones. This model suggests that events within the loop can influence their own past to avoid logical inconsistencies, and each interaction within the loop must self-consistently support this. The circumstances that gave rise to it provide an intriguing look at a paradox-free framework for time travel. For instance, if particles in a quantum system were to travel through time, they could interact with themselves from the past to make sure that the results line up perfectly without breaking causality. These concepts aren't just theoretical musings. They've sparked computational simulations, studies, and experiments to model particle behavior in closed timelike curves. Behave if subjected to time loop-like conditions. The results suggest an elegant consistency. For instance, particles might interfere with their past iterations in a manner that obeys the laws of quantum mechanics, while preserving their physical properties. These findings bolster the idea that under the probabilistic umbrella of quantum physics, the seeming contradictions associated with closed timelike curves may dissolve. What's even more fascinating is the potential role of these principles in advancing. Fields such as quantum information and computation have theorized that hypothetical quantum systems with closed timelike curves could solve some computational problems exponentially faster than classical systems. This has sparked an intriguing interest in potential applications beyond theoretical physics. But as fascinating as these ideas are, the difficulties in implementing them are enormous. Fortunately, Gödel Tipper has proposed some solutions. We are still a long way off from being able to manipulate space-time in a way that would meet the demands of these theoretical models, which are based on extremely specific and often unrealistic assumptions. Even within quantum mechanics, there are exciting theoretical frameworks and simulations that hint at these possibilities, but we still have a long way to go before we can put them into practice. All of this highlights how humbling it is that we are still a long way from truth about our present knowledge of closed timelike curves. They may be a good place to test the limits of physics, but we won't have any practical use for them for quite some time. This is a sobering reminder of how little we know about the cosmos, but it's also a source of inspiration. Studying these curves goes beyond the goal of solving time loops. It forces physicists to reconsider the basic laws controlling space and time. Through their investigations into probability, causation, and the relationship between macroscopic systems and quantum phenomena, physicists are shedding light on the nature of reality, improving our understanding of general relativity, making strides in quantum computing, and reshaping cosmology. Studying closed, timelike curves has far-reaching effects, impacting many fields and influencing the future of science. Time travel has long captivated humans, with wild tales of stepping into other eras and complex theories examining its scientific plausibility. The idea of breaking free from the constraints of time and witnessing history firsthand has always sparked our imaginations. Now, with the help of modern scientific advancements, we can finally answer the fundamental questions that have defined human curiosity for millennia. Exploring one of the most ambitious frontiers in theoretical physics, the construction of a quantum time machine. To grasp the essence of this potential achievement, one must first understand the theoretical foundation behind time. Is it just fiction, or is science actually holding the blueprint for what could become the greatest technological breakthrough in human history? Space-time, according to Einstein's revolutionary theory of general relativity, is like a stretched rubber sheet. When heavy objects, like a bowling ball, press down on it, smaller objects roll toward it. Now, picture this. You can create a space so distorted that it curves back on itself, connecting faraway points across it. This isn't just a thought experiment. It's the theoretical basis of the wormhole. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical structure that could connect two seemingly unrelated points in space and time. The idea of a wormhole, a tunnel that could cut through the universe, sounds appealing, but the reality of building or maintaining such a bridge is incredibly complicated. Wormholes are thought to be inherently unstable, with the potential to collapse almost immediately after formation. In order for one to be passable, a mechanism would be required to. The door opens to exotic matter, a hypothetical substance with a negative energy density that could resist the forces of nature that are trying to close the wormhole. However, this is no ordinary substance. Its very existence challenges the accepted laws of physics, and one of the greatest obstacles to its creation or use is the concept of quantum. With this, the spotlight moves to quantum physics, which may hold the key to overcoming these obstacles. Quantum systems, with their paradoxical behavior and vast computational potential, may hold the key to creating and controlling negative energy on a large enough scale to support these space-time conduits. One example is the Casimir effect, which is the attractive force experienced by two closely placed, uncharged parallel plates due to fluctuations, which are transient and energetic ripples that can even occur in a vacuum. This negative energy is essential for stabilizing wormholes. Although the Casimir effect has been successfully demonstrated on a small scale in a laboratory, turning it into a practical energy source to keep space-time open would necessitate unparalleled innovations in quantum mechanics and experimental creativity. If this kind of quantum phenomenon can be extended to bigger systems, it could theoretically help stabilize wormholes. When it comes to quantum field manipulation, if quantum systems are going to provide solutions, then quantum computing could be the way to go. Unlike conventional computers, quantum computers don't limit themselves to binary states, so they can simulate the curvature of space-time and run computations on an enormous number of possible outcomes at once. This opens the door to new breakthroughs in the modeling of complex phenomena. Quantum systems are making theoretical proposals in quantum gravity, which connect the tiniest quantum scales to Einstein's bigger relativistic picture, computationally approachable. This work is still in its early stages, but it shows the promise of quantum computations and the ability to understand and manipulate the fundamental elements of space and time. Changing gears, one of the most fascinating breakthroughs in quantum physics is the discovery of time. A system that can create stable repeating loops in both space and time could open up new possibilities for manipulating the passage of time. Unlike regular crystals, which repeat their structures in space, time crystals exhibit oscillations that contradict one of the fundamental laws of physics: energy conservation over time. Time crystals can oscillate endlessly between states without losing energy, which was previously considered impossible. Specific areas where time laws deform or break up, opening up new avenues for wormhole anchoring, wormhole guidance, and controlled space-time anomalies. While the practical uses of time crystals are still in the realm of speculation, recent exciting laboratory experiments have shown that time crystals do, in fact, exist under very controlled conditions, paving the way to investigate their potential functionalities. One particularly intriguing idea is to stabilize time phenomena that are prone to oscillations, providing a means for the maintenance of specific time loops that are essential for accessing different points in the space-time continuum. These theories are still in the conceptualization stage, but they hint at a future ripe with experimentation and discovery. Another quantum phenomenon that is relevant to these theories is quantum teleportation. As a fundamental aspect of quantum mechanics, teleportation describes the immediate transfer of quantum states from one location to another using entangled particles. Transmitting information or states from one location to another, regardless of physical distance, raises intriguing questions about the nature of time and space itself. What if, instead of focusing on classical data transfer, researchers in the field of quantum teleportation investigate the potential for time entanglement, which would link quantum systems not by physical distance, but by temporal separation? This line of inquiry calls for rigorous mathematical analysis. Imagine a world where time and causality are no longer fixed concepts. Instead, entanglement can span across vast distances, connecting the states of particles in the here and now with those from days or centuries ago. This would open up exciting new avenues of theoretical interaction across the ages, but it also raises questions about the practicality and desirability of such a concept. Could changing the inherent symmetry of time cause paradoxes? Would these endeavors be worthwhile if they succeeded? When put together, the concepts of wormhole stabilization, quantum fluctuations, advanced computing, time crystals, and quantum teleportation form an enthralling avenue for future exploration. While these questions do not yet have clear answers, they do represent pieces of a bewilderingly complex puzzle that humankind is constantly trying to understand and shape in relation to the universe and the continuum of. Time travel is a fascinating concept in science fiction. It offers a glimpse into a world where the lines between the past, present, and future blur. The question is, can it transcend science fiction and become a reality? Many intriguing questions remain unanswered, but technological advancements in this area are leading researchers closer to a solution. Time travel, once the domain of science fiction and blockbuster movies, has recently begun to make its way into academia, prompted by new findings about the complex relationships between quantum entanglement and the structure of spacetime. To investigate this, we must first imagine a universe where the manipulation of microscopic particles grants us unprecedented control over the fabric of spacetime. Could quantum mechanics hold the key to this utopian dream? Behold the remarkable phenomenon of quantum entanglement, which happens when two particles interact in such a manner that the states of one particle become instantly linked to the states of the other, regardless of their distance from each other. It's as if the universe has bestowed this extraordinary behavior upon these pairs of particles, leading Einstein himself to coin the term spooky action at a distance. At first look, this appears to contradict. Although it may seem obvious, entangled particles can perceive the actions of their paired counterparts across great distances. This perplexing relationship has been confirmed time and time again by experiments, expanding our knowledge of the laws of the universe. To illustrate, consider a scenario where two sets of gloves, one for each hand, are sent to opposite sides of the Earth. As soon as you open one set of gloves and see the left hand, you will know that the other set of gloves is inside the other set. However, there is a catch that makes entanglement so remarkable. It's extraordinary how quantum particles not only know their state in advance, but their measurement also affects the state of neighboring particles in the same instant. It's as if these particles are constantly dancing in a way we can't yet fathom. Things get even more interesting when we include Einstein's theory of general relativity. GR describes the cosmos as a four-dimensional fabric of spacetime. Within this framework, there's a concept called wormholes, which are also called Einstein-Rosen bridges. These hypothetical tunnels through spacetime could connect two distant locations or even different points in time. To visualize it, think of spacetime as a two-dimensional sheet of paper. If you fold the paper so 2 points touch, then punch a hole through it, you've created a shortcut. In theory, wormholes could work in a similar way on a smaller scale. Why is this important for entanglement on a cosmic scale? Well, it's all part of the ER-EPR conjecture, which was proposed by Einstein, Nathan Rosen, and other early quantum mechanics pioneers. It suggests that every pair of entangled particles could be linked by a microscopic wormhole, which would explain both the enigmatic connections between entangled particles and the structure of wormholes, which are hypothetical shortcuts through spacetime. Imagine a web of interconnected spacetime threads, each representing a connection between two entangled particles. If you were to follow a thread from one particle to the other, it could loop through a tiny wormhole. Could this mean that we could use entanglement to travel backward or forward in time through these wormholes? It's a crazy idea, but it could lead us to a deeper understanding of the laws governing the vast cosmos and the mysterious quantum world. The link between entanglement and spacetime extends well beyond theoretical conjectures and into the realm of advanced experiments. Thanks to groundbreaking technologies like quantum processors, scientists are able to simulate and investigate these theories, which provide a theoretical framework connecting two of the biggest puzzles in physics: general relativity and quantum mechanics. However, the greatest challenge in modern physics is experimentally verifying such an idea. Unprecedented connections. For example, scientists have used entangled photons to see if changing the behavior of a single particle changes the shape of spacetime. Their preliminary results suggest that entanglement may have an impact on the universe's fundamental structure, but there's still a long way to go before we can confirm these findings. Nevertheless, it would be incredible to have the means to probe the fabric of existence, a capability that seems more like magic than science. But there are still huge obstacles to overcome. The creation and maintenance of sufficiently large-scale entanglement to test the EPR conjecture is an enormous technical challenge. Because quantum states are very sensitive and can be broken by very small amounts of external energy, these experiments necessitate very exacting conditions and equipment. Moreover, although we can model certain parts of quantum mechanics and general relativity using sophisticated algorithms, there is presently no practical method to manipulate entangled particles to generate order. Although the concept is based on speculation, it is not completely without merit. For instance, some physicists believe that if we could stabilize and control the connections represented by the ER-EPR conjecture, we could access certain regions of spacetime that would allow us to navigate faster through the universe or even through time. The potential implications of this theory are too appealing to ignore. Be otherwise unattainable, it's a fascinating and exciting prospect to think about. Of course, there are a lot of philosophical and scientific questions that come up when considering the idea of time travel enabled by entanglement. Could we visit the past without causing paradoxes? Would future civilizations seem to bring innovative technologies or warn about the dangers of abusing such power? Although these questions may sound science fiction, they highlight the profound implications of investigating these concepts. Propels us towards the music solutions. Quantum entanglement is a phenomenon that explains some of the universe's most perplexing mysteries. The idea has piqued the interest of both scientists and laypeople who are wondering what part it plays in space travel, time travel, and the very nature of reality. Starting with the idea that entangled particles can communicate instantly across great distances, which goes against the traditional rules of locality, we are on the verge of a better grasp of. The idea of exploring time travel through quantum mechanics is no longer limited to science fiction. With recent advancements, we can simulate scenarios that were once thought impossible. For example, in Einstein's theory of general relativity, there is a concept of a particle traveling backwards in time through a closed timelike curve. This concept raises profound questions, such as whether this could lead to paradoxes like the grandfather paradox. By harnessing quantum systems, researchers have discovered ways to model time travel scenarios that avoid conventional paradoxes by utilizing quantum entanglement and superposition. Two quantum computing titans, Google and IBM, have made great strides in modeling these mechanics with their quantum processors, which could lead to a resolution to the particle's ability to alter its own past. Simulations using IBM's quantum computers have shown particles navigating closed timelike curves, which has helped us understand how these systems behave in different environments. One example is retrocausal systems, where the roles of causes and effects seem to be reversed. ERS has studied these systems and found that particles can choose their states consistently without breaking any quantum mechanical laws. This suggests that retrocausality is real. It is unlikely to produce paradoxes, but it may function within a framework that has not been completely elucidated. In a similar vein, the quantum team at Google conducted experiments to study the complex dynamics of entanglement across time. By simulating situations in which particles could interact with their past or future selves, the team uncovered insights that question our conventional notions of linear time. The ramifications of this finding are enormous. These experiments provide more than just proof of concept. They broaden the horizon of what could be technically feasible in the future. While the idea of retrocausality is controversial, recent developments in modeling retrocausal systems have transformed skepticism into fascination. Retrocausality is the idea that effects can occur before their causes, which challenges our traditional view of cause and effect. Researchers in the field of quantum simulations now have the means to put these outlandish theories to the test in safe environments. For example, simulations show that particles subjected to retrocausal effects can behave in a way that seems to predict future events without compromising the quantum state stability. This lends credence to the idea that retrocausality isn't always a threat to nature, but may actually be an inherent. In contrast to classical systems, where changing the past would invariably result in inconsistencies, quantum systems appear to adapt dynamically. Particles can exist in multiple states simultaneously until they are observed, which allows them to circumvent paradoxes. This flexibility could explain how particles avoid contradictions when looping through time. Imagine this as a quantum choose-your. It is impossible to overestimate the importance of entanglement in these situations. When particles become entangled, their properties become interconnected regardless of the distance between them. This entanglement persists even when one of the particles is subjected to external forces, proving that quantum mechanics can transcend classical limitations and provide elegant solutions. Regarding interactions that mimic time travel, studies have shown that entangled states could be the secret to maintaining consistency across different times. It's like particles communicate through entanglement to keep their shape-shifting quantum states invariant, which strengthens the system. However, this interconnectedness also begs the question of whether time is an emergent property of the universe's quantum state. The intersection of quantum computing with these theoretical frameworks has ushered in a new age of discovery, with tech giants like Google and IBM not only pushing the limits of quantum hardware, but also giving us the means to investigate the age-old philosophical mysteries. With quantum processors, we can run calculations that would take classical supercomputers millennia to finish, and researchers can model interactions and entanglements on a scale never before seen. In addition, as our knowledge of quantum systems grows, we are seeing how classical physics has its limits, how traditional models can't capture the subtleties of time and causality as shown by quantum mechanics. The quantum realm, with its seemingly contradictory principles, is making us reevaluate our very reality. With energy states fluctuating, particles behaving probabilistically, and information flowing in ways that seem to defy macroscopic time, as we know it, might just be one of many dimensions. The apparent linearity is a result of the scale at which humans operate within the quantum domain. Time could loop, branch, or dissolve entirely, weaving a web of temporal possibilities. Another fascinating result of these developments is the possibility that they will bring together, for the first time, previously separate ways of understanding spacetime. Theories that have sought to reconcile quantum mechanics with general relativity have traditionally confronted difficulties, especially with regard to the quantum scale interactions of gravity. But new frameworks introduced by studies of entanglement and retrocausality could fill these gaps. Some researchers have even speculated that spacetime could arise from the entangled structures of quantum states. If this is correct, it could pave the way for the long-sought theory of quantum gravity.